Hello everyone, welcome to my civil engineering YouTube channel. Please subscribe to this channel and hit the bell icon to get notified when I post my new videos. So today I'll be discussing a numerical on how to determine slope and deflection for a simply supported beam using moment area method. So here basically I have considered a simply supported beam AB wherein the span is equal to 6 meters and it is loaded with UDL of 12 kilonewton per meter magnitude, which is at the span of 3 meters, and then it is also loaded with 9 kilonewton of concentrated load, which is at the distance of 4 meter from the left support A. So before determination of slope, so here basically we are supposed to determine slope at A and deflection at point C. So before determination of the slope at A and deflection at point C, so we are supposed to determine the support reactions which are caused due to the application of the external load, that is 12 kilonewton per meter of UDL and 9 kilonewton of concentrated load. So for determination of support reaction, we are supposed to apply the equilibrium conditions. So first and foremost, equilibrium condition is sigma h, that is summation of all the horizontal forces is equal to 0. Since you can just observe over here, you don't have any horizontal forces over here, so automatically the first equilibrium condition is satisfied. The second equilibrium condition is that the vertical equilibrium condition, that is summation of all the vertical forces, will be equal to 0. So here the upward forces is considered to be equal to that of the downward forces. So there are two upward forces in the supports. So one is VA and another is VB. So VA plus VB is equal to 9 plus 12 into 3. So 12 into 3 is nothing but we need to convert the UDL to the point load. So therefore, in order to convert UDL to point load, we are supposed to multiply the magnitude of the load to the span to which the load is acting. So 12 is the magnitude and span to the UDL acting is 3 meters. So 12 into 3 comes on to be the conversion of UDL to the point load. So it is 12 into 3 plus 9 on to be 45 kilonewton. So VA plus VB will be equal to 45 kilonewton. So next comes on to be the equilibrium condition applied for the moment. So here we just we can straight away tell as the clockwise moment are considered to be as positive and anti-clockwise moments are considered to be as negative during the application of equilibrium conditions for the moment. So but we are our main motto in this step is to determine the support reactions. So therefore, in order to apply the equilibrium condition of the moment, we are going to consider the reference point at either of the supports, either at A or at B, not anywhere at the midpoint. So therefore, in order to determine the support reaction, we can take the moment at any one of the points, either at A or at B. So I'm just considering the moment about A point. So here clockwise is considered to be as positive and anti-clockwise moments are considered to be as negative. I just start from point B. So VB into the distance, force into perpendicular distance. So VB into the distance between B to A, the perpendicular distance between B to A is 6. Since it is acting in anti-clockwise direction, hence it is considered to be as negative. So V minus VB into 6. So next comes on to be 9 kilonewton force at the distance of 4 meter from A. So 9 into 4 meters, which is acting in clockwise, hence it is positive. So next is 12 kilonewton per meter. So this is a UDL which is acting. So 12 kilonewton is acting at the distance of 3 meters, and always we can straight away tell as the UDL is concentrated exactly at the centroid. I mean, the influence of the magnet, there is a much more or higher degree of influence of the UDL exactly at the centroid point itself. So therefore, we are supposed to multiply this load to the span to which it is acting and then convert that into the point load. and then we need to place it exactly at the centroid distance, means it is 1.5 and 1.5 meters, means the point load of 36, that is 12 into 3 will be 36 kilonewton, will be exactly acting at the distance of 1.5 and 1.5 meters. So therefore 12 into 3, multiply the distance between the load to the point A is 1.5, so it is 12 into 3 into 1.5, equate that to 0, you will get the value of VB as 15 kilonewton. So after determination of VB, so if we just substitute that value in the vertical equilibrium condition, we'll get the value of VA as 45 minus 15 as 30 kilonewton. So that is the value of VA and VB, and this is how we can determine the support reactions by using the equilibrium conditions. So next step is sketching of the bending moment diagram. So this is a very important step. So as in case of determination of slope and deflection by using the moment area method. So this moment area method is based on the bending moment diagram, area of the bending moment diagram. So therefore sketching of the bending moment, determination of the bending moment and sketching of the bending moment diagram is very important step over here. So here we have divided this step into 3 parts. So first one is since we have 2 forces over here, so in order to sketch the bending moment diagram by considering overall forces into consideration, it becomes difficult for us to solve the problem. So therefore we are taking the forces at a single stretch, one by one. So therefore firstly I am going to consider the bending moment calculation only by considering the support reaction. So this is the way I have considered without any external load, only due to the support reaction. So since we have been asked to find out the deflection at C and slope at A, so only at those 2 points I am going to determine what are the bending moment values. So I just start from point B over here. So what is our deflection, what is the bending moment due to the VB I am going to determine over here. So VB into the distance between B to C is 3 meters. So VB into 3 is VB is 15 kilonewton, which I have got it from the previous slide. So 15 into 3 comes on to be 45 kilonewton meter. So since it is acting in anti-clockwise direction, so here before going to the actual bending moment calculation, so I just take come to the sign convention over here during the calculation of the bending moment. So if we are going from right hand side, the bending moment is if at all, if it is in anti-clockwise direction, it is considered to be as positive, and if it is in the clockwise direction, it is considered to be as negative. And same in the left hand side, it is considered to be the reverse sign as that of the right hand side. So here as in case of C, we have VB into 3, which is acting in the anti-clockwise direction, hence it is considered to be as positive and it is drawn above the baseline. So next is I need to calculate the bending moment at point A due to VB. So VB into the perpendicular distance is 6. So VB into 6 comes on to be 90 kilonewton meter. So if I just draw a line over here, so this represents the easy solution for the deflection and slope. So this overall triangle will be divided into three substructures. So this is a small triangle, and this is a rectangle, and this is a another triangle. So next comes on to be calculation of the bending moment due to the load of 12 kilonewton per meter UDL. So here we have taken into consideration of the UDL of 12 kilonewton per meter. So here we are supposed to calculate the moment about A. So it is 12 into 3 into 3 by 2 comes on to be 54, which is acting in clockwise direction, hence it is considered to be as negative, and it is drawn below the baseline. And since it is a uniformly distributed load, the variation is parabolic, hence it is drawn as a parabolic curve. So next comes on to be the next bending moment sketching is due to the load of only 9 kilonewton concentrated load. So the moment of 9 kilonewton at point C is 9 into distance between D to C is 1 meter. So 9 into 1 comes on to be 9 itself. So which is acting in clockwise direction. Hence it is considered to be as negative, and the variation of bending moment due to the concentrated load is linear, hence it is joined as a straight line. So next is bending moment at point A. So it is 9 into the distance between D to A is 4 meters. So it is 9 into 4 comes on to be 36 clockwise, hence it is taken as negative. So this is all about sketching of the bending moment diagram due to the by taking the individual load into consideration for easy calculation of slope and deflection. So next comes on to be calculation of deflection of at point B. So here this dotted line of dotted line of red color represents the deflected position of the beam, and if I just draw the center tangent over here through A, it meets at the point B, if I just draw the distance, it comes on to be dBA. So dBA represents the deviation of B with reference to A point, and then theta A represents the slope which is caused due to the deflected position of the beam due to the application of load. So here dBA I am supposed to calculate. So dBA is nothing but the area of M by EI diagram between B to A, means the overall beam I am going to consider, into the centroidal distance. So here area of M by EI diagram between A to B is nothing but this overall bending moment diagram what I have sketched. I need to consider all the areas of the individual sketches, and then I need to multiply with the centroidal distance with reference to the point A, So in the first sketch, I just divide this as 3 substructures, 1, 2 and 3, 2 triangles and 1 rectangle. And then in the second subsketch, it is the parabola, so wherein its area will be equal to one third of base into height. And then in the third subsketch, if I just divide it, it will be 2 triangles and 1 rectangle. So if I just apply the area formula for each and every respective structures, and then multiply with that of the centroid from that of A as a reference point, I'll get the equation as this fashion, and then I'll get the value of dBA as 460.5 divided by EI. So this is all about the calculation of deflection at point B. So next comes on to be slope at point A. So we need to calculate the theta value here. So here if I just project this, it forms the triangle. This is dBA and this is 6 meters and this is theta A. So tan theta, if I just apply the application of the trigonometric tan function, it will be tan theta A is equal to dBA divided by 6. Since theta is very small, tan theta A will be equated to theta A. So dBA I have got it as 460.5 divided by EI. So overall divided by 6. So it comes on to be 76.75 divided by EI is the value of slope at point A. So next comes on to be determination of deflection at point C. So here C1 represents the final point, and CC1 is the deflection due to the application of load. So C represents the initial point and C1 represents the deflected point. So here my motto is to determine what is the distance of CC1. So I can just make that as CC1 is equal to CC2 minus C1 C2. So here CC2, if I just draw here by projecting this is CC2 and this is A and this is theta A. So this CC2 and this is span is equal to 3 meters. So here the CC2, this bending will be in terms of the arc of the circle. So therefore the CC2 is equal to the product of span multiplied with that of the slope. So therefore it is equal to, span will be equal to 3 meters and slope is equal to theta A. So it is 3 times of theta A. 3 times of theta A is equal to CC2, and C1 C2 is deviation of C with reference to A. So in order to determine deviation of C with reference to A, it is nothing but the area of M by EI diagram between C to A, the area of M by EI diagram between C to A, and multiply with that of the centroidal distance. So then here as in case of the bending moment sketching in the previous slide which we have drawn, we need to consider only the respective shapes of the bending moment diagram between A and C point itself. So between A and C point, what all the respective shape of the bending moment are there, only that we are supposed to consider. So and then we need to multiply that with the individual centroidal distance with reference to point A. So if I just take this as the things, so and then substitute the values, so I'll get CC1 as 135.75 divided by EI. So this is a value of deflection at point C. So here in this video I have determined what is the value of theta A and also what is the value of deflection at point C. Thank you for watching. Please like, share and subscribe the video. Thank you.